Hello, welcome back to Math 332 Linear Algebra, and welcome to Chapter 2, where we're going to talk about the concept of determinant of a matrix. So the determinant of a matrix is a number assigned to a square matrix. So a square matrix obviously have a lot of different entries in it, but we are going to forget about those entries and basically assign a particular number to represent that matrix. So every matrix will be reduces to a number. Every square matrix will be reduces to a number, and we're going to use that number mainly to determine whether or not that particular square matrix is invertible. So we have 4 different videos assigned for this particular topics. And the first video, we are going to talk about how do you actually compute the determinant of a matrix. And then we are going to spend 3 videos to talk about various property of determinant, and very importantly, to somehow show that and prove it to you that we can use that number to determine, completely characterize whether or not a square matrix is invertible. So we're going to look at all that, and this is going to be the first part of the presentations. All right, let's begin by looking at the objective for this particular section. So at the end of this sections, you should know what is a minor and what's a cofactor for a matrix. Obviously, you need to know how to compute the determinant of a matrix by doing something that we call the cofactor expansion. And at the end, you should also know what are the determinant for a diagonal, upper, and also lower triangular matrix. All right, so let's look at a 2 by 2 matrix. So you have a 2 by 2 matrix. We are going to call this number here as the determinant for this 2 by 2 matrix. So this number AD, okay, minus BC is known as the determinant of a 2 by 2 matrix. And notation wise, you can write it like this, or you can write it like this, okay? And some of you, in fact, many of you, I think, have seen this kind of determinant for a 2 by 2 matrix before in the context of the formula for the inverse of a 2 by 2 matrix. So if you have ever seen a 2 by 2 matrix inverse formulas, you will come across something called a determinant. And as you can see, this formula is pretty neat. Eventually, we'll develop a formula that kind of looks like this for any n by n square matrix. So you know that previously we have seen in the previous video, we can find the inverse of a matrix by going through the row reductions. We can also do something called the adjoint methods, and you can get formula like that through the adjoint methods. We will talk about this at the end of this chapter. But what I'm saying is that many of you have seen this particular number determinant in the context of this formula for the inverse. And also, as you can see, because we have 1 over it, so you know that the determinant of A, if it is not 0, then the inverse for this 2 by 2 matrix is given by this particular formula here. Okay, and what we want to do is to expand this concept of determinant to any square matrices of size 3 by 3, 4 by 4, 5 by 5, so on and so forth. All right, so I want to do more than just looking at the determinant of a 2 by 2 matrix. So in order to do that, we will have to go through some terminology. The concept of minor and cofactor, which is what we're going to look at it here. So for a matrix, let's say, for example, this is a 3 by 3 matrix. So this is the entries of this 3 by 3 matrix. So every entries of a matrix will be associated with a number called a minor. Okay, so the minor of A11 is the number you obtain by crossing away the first row and the first column of this matrix. And as you see, if you do that, you have a smaller matrix, which we call a submatrix. So if you compute the determinant for this submatrix, okay, you will get the number which we call the minor associated for these entries A11. So the minors of A11 is given by M11, that's the notations, which is the determinant for this smaller submatrix right here. And since the submatrix right here is 2 by 2, we know how to compute that. That is A22 multiply A33 minus A23 multiply A32. So we know that. So every number has, every entries, every number right here has a minor associated with it. So for example, A12 has a minor associated with that entry. So how do you compute that? You cross away these entries, this particular row and this particular column. Again, you have a submatrix smaller matrix. This case, your submatrix is 2 by 2, and we can again compute the determinant of this 2 by 2 matrix. We will get the minor of A12, which we're going to denote as M12. So think of it like this. You will get a smaller matrix. The submatrix will be something that looks like this, and then the minor of A12 will be this A21 multiply A33, and then A31 multiply A23 and subtract them, and you get that. Okay, so I think you see the pictures. So let me rewrite this. This is 2, 2, and then this is 3, 2. So A33 will have a minor, and that minor is a determinant of this submatrix, so on and so forth. Okay, so now every entries here has a minor. Okay, so that's the minor. So every Aij has a number associated with it, which is called Mij. Okay, so that's minor. What is cofactor then? So cofactor is easy. So cofactor for any entries is basically so let me write this thing down again. So every entry here has a number associated with it, which is called a minor. Every number here also have another number associated with it, which is called the cofactor Cij. And the way we define Cij is nothing but a sign. Okay, so that sign here is either positive or negative, and you take that sign, multiply the minor Mij. So that's Cij. The cofactor for these entries Aij, which is known as Cij, is computed this way. Okay, so that's how you compute it. All right. Okay, so if you look at A31, for example, okay, so A31, right? Okay, so let's look at this. So A31 has a minor, so but if we look at the cofactor C31, that will be -1 to the power of 3 plus 1 multiply M31, and since this is 4, so the cofactor C31 is actually the minor M31. They are the same. But if you look at C32, so this will be -1 to the power of 3 plus 2 M32. So this is going to be negative. So you will get that C32 is negative of M32. So the cofactor is basically a sign, okay, a sign minor. So a minor that is associated with a positive sign or associated with a negative sign. So let's look at an example right here. So you have a matrix A3 by 3. So if you want to compute the minor of A11, you cross away first row and first column. You have this smaller matrix, 2 by 2, which we know how to compute the determinant. And the cofactor is a sign minor, which means that you multiply either a positive 1 or negative 1 right in front of M11. And in this case, as you can see, you are multiplying a positive 1 right in front of it. So you have M11 equal to 16. Okay, so that's how you get the minor for A11 and the cofactor for A11. Let's pick another entry. So every entry has a minor and cofactor. So 3, 2 is right here. So the 3, 2 is here, third row and second column. So again, cross away this third row and second column. You have the smaller submatrix, 3, 2, and -4, 6. Again, you compute a determinant, you get 26. If you compute the minor, sorry, the cofactor, right? So if you compute the cofactors, you will have to introduce this sign. That sign is -1, so you will get -26. So the minor is 26, but the cofactor is -26. We can do that for 4 by 4 matrices also. Everything's still the same. You just have to figure out how to compute the determinant for a 3 by 3 matrix, which we will know how to do it soon. So again, it's 2, 4. So second row, fourth column. So what you get, the smallest submatrix is 3 by 3. If you compute the determinant, that is what you get. And you know how to compute the determinant later. Right now, you just probably still don't really know how to do that yet. Don't worry. Trust me, the answer is 19. And then the cofactor is going to be this. Multiply M24, which you get 19 also. Okay, so now we know what minor is and what cofactor is, okay? Now, this theorem tells us something pretty cool. All right, I want you to read this theorem. If you don't understand what this theorem tries to say, you can look at this example. So this theorem says that for any n by n matrix, okay, so it's for any n by n matrix, but I'm lazy. I'm not going to write down the n by n matrix, so I'm just going to write down a smaller matrix. Let's say it's 3 by 3. Okay, so we have a 3 by 3 matrix A. So if you take these entries A11, right, multiply with the cofactor associated with this entry. So we are not looking just the cofactor, we are looking at the product, okay, of the A11 together with its cofactors. So if you do this and you look at the second entries, take these second entries, multiply the cofactor associated with it, and take these entries, right, and multiply the cofactor associated with it. And if you sum it up, let's say you get the number alpha. Okay, so if you sum it up, you get a number, let's call it alpha. Okay, now what the theorem say is that if you so take another row, so just now we are taking the first row, right? So if you take the second row and do the same, so take A2, so take A21, multiply with the cofactor C21, take A22, multiply with the cofactor C22, A23, multiply with the cofactor C23. If you sum it up, you will also get the same number alpha. That's what the theorem tries to say. And the theorem say a lot more than that. It says that if you do it in a third row, okay, if you do the so-called expansion, this is called the cofactor expansion, by the way. So this is called the cofactor expansions. And if you do the same thing, you do the cofactor expansion on the third row, you can see that this number will add up to the same number alpha. Now, forget about the row. Let's do the column. So you take A11 multiply the cofactor, A21 multiply the cofactor, A31 multiply the cofactor, you get the same number alpha also. So you do this column, do this column, do this column, which is right here, right here, right here. It will be the same as if you do the cofactor expansion on the row. They all add up to the same number. So not only true for the 3 by 3 matrix here, it's actually true by all the n by n matrix. That's what the theorem said. We're not going to prove it, but that's what the theorem said. And because of that, this number here is very, very special. We're going to give you a very special name for that. And as you can guess, this is defined as the determinant for this matrix. So every matrix, if you do this kind of expansions, you don't have to do all of them, obviously. They are all going to give you the same number. But if you pick one of the row and do this expansion, or pick one of the column and do the expansions, you get a number, and that number is defined as a determinant, okay? And that is called the determinants of the matrix A. And as you can see, no surprise that you can do it either by the column or by the row. You do exactly the same thing like that. Associated every cofactor with these entries, you multiply them and sum them all up, you will get a number, and that number will be the same no matter how you do it, by the row or by the column. Doesn't really matter which one, but you can change row and column in the middle though. So if you do it second row, you have to be second row. You do it a third column, you have to be all on the third column. Then we get a number called a determinant, okay? And obviously, because of that, you have a matrix A and matrix A transpose. If you compute a determinant, obviously they are going to be the same, because the row expansion here is the same as if you're doing the column expansions, and obviously they're the same. How do you know they are the same, by the way? You know they are the same because of this theorem. How do you prove this theorem? We're not going to go into that, but if you trust it, this is a mathematical theorem. Obviously, this is true. You can look at the proof. And the theorem says that it doesn't really matter what you do, you get the same number, and that same number is called the determinant of that matrix A. All right, let's look at some computational examples. So you can apply the concepts of a cofactor expansion of a 2 by 2 matrix. You will get the same numbers that you know from before, so that's no biggie. And let's look at another example, a computational example right here. And let's say we choose the first row, okay? So we do the first row. So you take, so this is a A11, right? So this is 1, multiply with this cofactor. All right, and then it's 5 multiply with this cofactor, all right, and then plus 4 multiply with this cofactor. So this cofactor right here is the minus 1 to the power of 1 plus 1, the minor 1, okay, and plus 5, okay, multiply the sign, right? So this is going to be 1 plus 2, and then the minor 1, 2, and then plus 4, all right? And then it's negative 1 to the power 1 plus 3, and then the minor 1, 3. So you can see that this is just 1. This is positive 1, so you get this. This is minus, so you get a 5, 1, 2. And then you have a 4. This is positive 1, and then you have 1, 3. So what is minor 1, 1? Minor 1, 1 is the determinant of this, as you can see right here. what is minus 1, 2? Minus 1, 2 is the determinant right here, as you can see. And then what is minor 1, 3? Minor 1, 3 is this determinant right here. We already considered the sign. So the sign here is positive, negative, positive. And as you can see now, if you do this, you will get negative 9. So that is, by definition, the determinant for this matrix A. And obviously, you can choose by doing the second column. You can do the second column. And if you follow the same expansions, you will get this particular expression right here, which will also give you negative 9. And since this determinant is kind of invariant to which row or which column you choose, so obviously, actually, for simplicity, as you can see, your matrix A, the easiest way to compute this determinant is actually go through the expansion by the third row. Because if you do that, okay, you have this 0, you have this 0. You don't even have to compute what that minor is. You get negative 9 also. So sometimes which row to expand. Some people always expand through the first row because that's what they want to do. But sometimes it doesn't really matter because the matrix is complicated anyway. But if you have a matrix that has a lot of 0 on one particular row or one particular column, like this case right here, expanding through that row or through that column will be the easiest, okay? But still, it's up to you. We're going to get the number the same anyway. Okay, so obviously, we now observe that if you have a square matrix, if you have a row of 0 or a column of 0, immediately you know that that matrix, the determinant is 0. So say, for example, you have A, I don't know what that thing is, I don't care, but if you have like something that looks like this, entirely 0, you have a row of 0 or you have a column of 0, the determinant must be 0 because you can do the cofactor expansion across those row of 0 or column of 0, and obviously you will get a 0. Okay, so that's a very simple example. And actually, for some special matrices, like this one right here, this is called the lower triangular matrix. So this is the diagonal of a matrix. So for every square matrix, we have a diagonal. That's the diagonal of a matrix. And everything on the diagonal and below it, actually the definition is that everything above that diagonal has to be 0. Right here, some of the entry can still be 0, but it doesn't really have to be. But everything above it is 0. If you have something that looks like this is called a lower triangular matrix. This is a 4x4 lower triangular matrix. And what is the determinant for this? Well, see, as I said, we have a lot of 0. So let's say we choose to expand it through the first row. Then you will see that if you expand it through the first row, you have A1, 1, and then you have this minor, right? And then you have 0 and then some other minor, which is 0 anyway, so we don't care. So we get only this. And then go in, okay, kind of like do it recursively and start doing, concentrate on this determinant. Okay, so this is 3x3 now. I'm going to expand through this row again. So I have the A22 and then I have this minor, okay, as you can see right here. But the rest are 0. And then you have the 2x2 determinant where we know it's nothing but the product of these two. This one right here gives you 0 anyway, so you get something that looks like this. So you will see that the determinant for this lower triangular matrix is actually the product of all the diagonal entries. So the determinant for a lower triangular matrix is actually nothing but the product of all the diagonal entries. So this is not only true for upper triangular matrix, lower triangular matrix, or even diagonal matrix. The determinant is actually just nothing but the products of the diagonal entries. So for example, if you have 1, 0, 0, 0, 2, 0, 0, 0, 3, so the determinant is a diagonal matrix. So determinant will be 1 times 2 times 3, which is 6. Okay, so this is some special matrices which has a lot of 0. And very easily you can see that the determinants for this kind of matrices is nothing but the products of their diagonal entries. So make sure that you know, okay, what is the minor and cofactor and how do you actually do cofactor expansions using nothing but these formulas here. You can expand by the row or by the column. This is by the J column. This is by the I row, as you can see right here. Okay, so this gives you an idea how to compute the determinant of any square matrices. It kind of like define recursively. It's computationally, it's not so easy to do though. I mean, we know how to do it, but computationally it might be tedious. But now we know how to compute the determinant for this square matrix. Okay, we will look at why we care about this number in the next videos, and they have many special property for determinant. And eventually we'll see that we're going to use that number to tell us the invertibility, to give us information on the invertibility of a matrix. And actually, we also can develop a formula for the inverse, which involve the concept of determinants. All right, this concludes our discussion on section 2.1. And the next video, which is sections 2.2, we are going to explore various properties for determinants. In particular, we are going to look at how we can use row reductions to compute the determinant of a particular matrix. And we'll see you then.